Thank you. All right, so thank you for taking time to come and listen to my thoughts on insights from orthogonality for maths. So I'm a mathematician, so this is based within mathematics, but don't fear, I'm not going to bore you with too much mathematics detail. Starting off, in maths modules that we teach at university or even at school, we challenge our students to not only know that certain concepts or certain results hold, we want them to also know why they are the case, and we would also like them to know how to represent and reason more mathematically. Our students, however, they often are conveying their own individual understanding through pictures, through examples, perhaps through their own kinds of reasoning that's got no real link to mathematics. And through effective teaching and engagement with the rhetoric of mathematics, we try to shape the individual and intuitive representations and reasonings into more mathematical representations and reasoning. So in the talk, I'm going to propose a conceptual framework to empower students and also lecturers to make this transition. So that's the goal of the talk today. But why is this important? Well, unfortunately, as many as 90% of the prospective students for tertiary education institutions in South Africa have no more than an intermediate level of mathematical proficiency as measured by the national benchmark test. And over the past 3 years, one hardly sees much improvement in that. This leads to a discontinuity between the outcomes of schooling and the demands of higher education, and this is commonly known as the articulation gap. And this is understood to involve the depth of understanding, the depth of learning, and the level of competency with the acquired skills in mathematics. And it is also seen as a problem which affects the performance of our students at university. But as a gap, it's called the articulation gap, it can be closed from both sides. And I see this as opening up possibilities for positive action, as also referenced by the Department of Education. There have been some suggestions indicating that such a change to fill this gap would require less memorization, less repetition of facts, and the ability to think critically, independently, and thoughtfully. However, with no framework or no suggestions of how to do this, many of our students are still at a loss and are not really performing when they get to higher education. I'm going to argue that orthogonality is key to bridging this gap today. But before we can find a solution, we need to really understand what the problem is. So what is the essence of mathematical proficiency? Perhaps there are several binary oppositions at play, like do you have a mental visualization, or do you have a more physical interpretation? Do you prefer algebra, geometry? Do you think of it as a human activity or more of a mathematical idea? Is it more about knowledge or is it more about skills? But perhaps thinking of it in this way is a little bit too one-dimensional and immediately gets us into trouble, especially when you're thinking like a mathematician, because in the language of logic, binary oppositions form what is called a dichotomy, which essentially arises when you have two concepts that are mutually exclusive and jointly exhaustive. In other words, the one is the negation of the other, but none of these are negations of each other. So my suggestion is that mathematical proficiency is perhaps a little bit more nuanced, that we need to think of the essence of it in terms of what mathematical knowledge and how do we reason about it. But moreover than that, we don't think of them as binary oppositions, but we think of them as orthogonal to each other. And to this end, I've found that Mayton's legitimation code theory has been very insightful. So I'll explain this in my understanding of this framework. So it's an orthogonal framework. Our starting point is what is referred to as the specialization dimension of legitimation code theory. And this highlights that every knowledge, practice, belief, or claim is made about something, orientated towards something, and it is also made by someone. And you'll notice here, I'll focus only on the knowledge quadrant here. And the way that that one is characterized is that there is a strong relationship over here between the knowledge and the object of study, but a weaker relationship between the knowledge and the subject of the study, so the person who's doing that study. If you zoom in on this quadrant over here, you find there is another orthogonal framework, which is called the epistemic plane. And the epistemic plane, here on the vertical axis, we have what are referred to as ontic relations in this terminology, and that represents the strength of the relationship between a knowledge claim, so the knowing what, and the object of study. And then along the horizontal axis, what are referred to as discursive relations, that represents the strength of the relationship of referring to or dealing with the particular object of study. So this one over here. And when you put these two continua at right angles to each other, they produce 4 quadrants representing 4 different insights. And here this one referred to as the purest insight. Here there is a strong emphasis on the knowledge and also on the approach, on how you reason about the object. In the doctrinal insight, there is less emphasis on the knowledge, but there's a strong emphasis on how you do the reasoning, how do you refer to the object. And when you move to the left-hand side here, to the situational one, there's more freedom in your methodology, but there's still a strong focus on the knowledge. And in the knower, or the know insight, that's basically where anything goes. There isn't a strong emphasis on the approach or on the knowledge, but there's more of an emphasis on the individual who is engaging with this practice. All right, so that sounds all very delightful, but how does this come back to maths? So taking my own experience as a mathematician, but also as a mathematics learner many years ago, who did not find mathematics something that I could just absorb. I needed to really engage with it quite a lot. So I think I'm taking some of that experience and turning it into the following insight. So I'd like to take you on with a little example to begin with. If you take the idea of a knot in your shoelace, so some of you might have shoelaces, so now start looking at how do you tie your shoelace. We have several kinds of knots. So here is an example of what is referred to as a granny knot. If you unpack this more mathematically, so here I'm starting with looking at something that you see in every day, trying to represent it more as a picture, and you see different ways in which threads are tied over each other. You can go to a more mathematical representation by looking carefully as to how the lace is it going under or over, and you could even represent that really mathematically by capturing the various links that you have here and whether they're over or under. Looking at this in terms of knowing how, reasoning that here you know how without mathematical representation or reasoning, and on this side you're going to knowing how with more mathematics. If we take the vertical axis, there we're referring to what do we know. So one might say that if you look at these two pictures over here, you cannot, no matter what you do to continuously deform those, so you're not allowed to cut it, you're just allowed to move it around, you will never be able to deform this knot into this knot. They're two different knots there. But you can never be sure whether you haven't tried hard enough to do such a thing. However, if you go to mathematics, you can look at the polynomials that capture these links over here, and without a doubt one can see that those two polynomials are definitely not the same. So we've moved here from knowing that something is the case to actually knowing why it is the case, using more mathematical reasoning. So putting this all together, you have that this knot here, which is a granny knot, is a composite of two knots. So you take this picture, you cut it, you pull it apart, you can cut it, you get two composite knots here that are exactly the same. And when you multiply those two things obviously together, all right, you get another polynomial which captures the fact you have 6 links here, and you can get a different kind of picture of this which looks a little bit closer to the actual knot. Then as mathematicians like to do, you say, well, so what happens if I vary this polynomial, but now what I do is I take two different ones, all right? So I take the two going back here, so starting there, coming down here, I take two different knots, and I squeeze them together, and I get a new looking knot, which is represented in a different way geometrically like this, and you'll end up with what is referred to as a square knot. So the one knot is tying the right over the left, two in succession, and the one is right over left followed by left over right, and one is a more secure knot than the other. Well, what I've shown is that you can start off with something intuitive and move towards the mathematics, then start asking questions in the maths and going backwards, try and see what are you coming up with. So as my research methodology then, we have the distinction here between knowing what and knowing how. There are stronger ways of knowing what, and there are weaker ways of knowing what. The stronger, we know why a mathematical claim holds for a particular mathematical object of study. The weaker, it means we just know that it is the case. We haven't got a clue why. In terms of knowing how, the discursive relations, that's the horizontal axis. The stronger knowing how means that we're going to represent and reason more with mathematics. The weaker version is we know how without mathematics. So we can do it with our own intuitive, in our own notation or whatever we want to do. I'm not saying either of these is better than the other. This is also insightful at times. Another way to represent that using an orthogonal framework then is if I take those two continua, so here I've got the mathematical knowledge, the knowing what versus the know how. We once again get 4 quadrants, but I've labeled them somewhat differently to link up more with mathematics. So starting here in the doctrinal quadrant, I'm referring to this as procedural fluency because here you know the procedures, you know how. So you mostly know how to do routine things, but you might not necessarily know why you're doing those things. That requires more of a conceptual understanding. So you're knowing the how and you're knowing the why in mathematics. Over here you know why in maths, but sometimes you're encountering problems which are not necessarily represented so mathematically, but you will know enough maths to be able to move beyond that. And over here, there's absolutely no mathematical principles or reasoning or representations. All right. Now, for some examples, I've taken as examples 5 core areas, or I'm actually only focusing on 4 of them in this talk. I'll look at some algebraic processes, a bit of number sense, something about functions, and also trigonometry, something our students love to hate. And these are 5 core areas of mathematics that are also identified within the National Benchmark Test, and they do assess students on these particular competencies. All right. Okay, so if we take the example of multiplication, it's quite a routine problem. So if you give a student a question like multiply 6 by 53, there might be some people who would say, without a calculator, yeah, 6 times 50 plus 3, and they could work it out by seeing it's 300 plus 18. But do many of them know why that would be a way of reasoning? Well, some students might decide to think that when you're dealing with positive numbers and you're multiplying A by D, you're finding areas. All right, so here you could take A times by D, and you can split the D up into two bits, the B and the C. So taking the area of this rectangle is taking the sum of the two composite areas. And that's really what the mathematical distributivity law looks like. But if we give students this picture here, they really freak out and have no idea what we're talking about, but it's much more understandable in that context over there. Then one could take them to more non-routine problems. For example, set theory and logic then don't become so foreign if you understand these kinds of principles for multiplication and addition. So multiplication becomes replaced by the intersection and the addition by the union, and similarly for the disjunction and the conjunction. Another example is related to number sense. So here we're referring to equal to and less than. Now these are things that many of our students haven't really got their head around what they mean. They just see it as a symbol between two objects. But whether it's equal or less than or equal to, it's like very fuzzy kind of stuff. Little less do they know that in fact we are capturing a relation here between these elements, and this relation has particular properties, especially if it's an equal to. It has certain properties. If it's less than, it does not have all of those properties at all. And then if they don't fully understand equality as an example of such a relation, which we refer to as an equivalence relation, little do they know more about these other more complicated things. However, many students know how to work with the number line, maybe part of a ruler, yeah? Or they might be doing biology where they are classifying organisms based on certain kinds of properties. So they actually are forming equivalence classes when they are doing such classifications, and don't talk about mathematical language when you're doing this, but it comes quite naturally to them to reason in that way. So if we give them an example like solve the inequality 3 plus 4c equal to 10c, cancelling is usually the approach to follow there. And some students might try and draw a picture and see, okay, we're trying to find the intersection of two straight lines. Very few would say that actually we're applying some very interesting principles here of equality. So if A is equal to B, it doesn't matter what you multiply A and B by, that equality will remain the same. But if you move to inequalities, you have to be careful whether you are multiplying by a positive or a negative number. Stuff changes. So that means if you give them an example like solve this inequality, AB greater than or equal to 3B, they might really only remember those properties of equality and then just try to cancel and wonder why they've lost some of the solutions. So they really need to remember to follow cases. They might still follow an example, a reasoning process in terms of a graph by trying to say I've got one graph here which is a line 3x, and I'm trying to find the value A. So which of these, am I going this side of that graph or am I going that side? So they could play around with this to be able to find that answer. Still not doing like really neat mathematical reasoning, but some form of reasoning they're doing all the same. And then if you give them an example like this, which is totally different, totally non-routine, and ask them to say which of these statements over here are true, well then we just skip that one and move on perhaps, but they really need to understand then the number line. What are they dealing with here? What is a real number x that they have? And they need to be able to figure out how to reason, so based on things that they know, so from this sort of procedural space, which of the things that they've got a better conceptual understanding do they need to bring into this, and then still do some deduction. Functions. So functions, unfortunately, for some, it's the calculator. So at school, all they seem to do is plug into the calculator, and I like this quote that says here, I don't know what half of these functions do. Whereas when they get to university and engineering, it seems like half of the functions they need are actually not on that calculator. So this kind of mindset here kind of gives the feeling that a function is really just a rule, and if you give it an element of one set, it just gives you out exactly one element of another. All right? And you don't really worry what that answer is. If you plug in some numbers here, you don't really think. You just, that's the answer. Okay, so it's like a black box. However, mathematically, well, it's not really a rule. Rule is like, yeah, it sounds, yeah, it's just not mathematical talk, that. But it is, a function is really a relationship between sets, and we're assigning values in a very particular way. And with that kind of understanding that it's a relationship between things, one gets far more insight into moving beyond these kinds of functions. So sometimes you might have a function which has more than one value that it assigns to every value in x, or it could be that you have a function of more than one variable, so it's easier to move to functions of 2 or 3 variables. And if you're doing computer science, you might even be able to do functional programming with some insight as opposed to just blindly going along. Then one of the notions that we have with functions is that you can find the inverse. So if you have one function, how do you know that you have an inverse, a function that undoes that original function? So there's a nice procedure. Students can follow this procedure really neatly. But what's really happening over there is you're defining a new function, and there's a certain relationship between those values. More intuitively, you could draw it as one graph is the reflection of the other, or you could see it as, well, if I've got a temperature in degrees Celsius, I can find it in degrees Fahrenheit, and vice versa. So one function is reversed depending on which of these kinds of values you're given. So that's all fine and well. And then you hit them with an example, like this one. I know it's a rather toy example, but for the moment it serves my purpose. So you have a cycle shop that has 36 bicycles and tricycles, and collectively there are 80 wheels. And how many bicycles and how many tricycles are there? So I won't ask you to solve that. But many a time one might, first attempt would be trial and error, all right? So you might start off by saying, all right, I'm going to say 2 tricycles. I'm using the fact that the sum of these has to be 36. All right, and then working out the number of wheels that these would have. And then going through the process until I have 80 wheels. But, you know, how did I know I'm going to start with 2 tricycles as opposed to 2 bicycles? That could have been a much longer process. So then you need to be a little bit smarter and take this problem and say, well, actually, I'm going to call the bicycles the B's and the tricycles the T. So I use variables. That sum is 36, and this captures how many wheels there are. So I'm trying to solve a system of equations. Alternatively, I'm trying to find a matrix that is the inverse of this one, if one really understands some mathematics. So first of all, suppose we just take this thing over here. And I promised Hanley I'd bring some Excel into this after our discussion the other day. So some students will say, okay, I have a matrix here. I'm trying to find the inverse of that. And Excel taught me that there's something called M inverse. So if I just put my matrix in here, it should give me that inverse, and then I should be able to find my answer. Alternatively, you might know there's a procedure called Gauss reduction. So you take this one matrix, you do a whole lot of row operations, swap things around, multiply them out until you get this thing looking like the identity matrix, and then your answer here is your inverse matrix. So what on earth is, these are all procedures and sometimes using a computer. But what was happening here is we have a generalization of that inverse that we had of a function. And the inverse matrix, so here we have AX is equal to Y. And we're trying to find another matrix, so we multiply both sides by that so that we get rid of this thing here. We say X is equal to this new matrix times by Y, and that gives us the answer. Yet other ways of finding this, if you don't do the Gauss reduction, you can use what we refer to as determinants. So being smarter with the maths, knowing why, knowing what methods to use, saves yourself maybe a lot of time. These are not wrong, but they give you some feeling of what's happening. We would like the students to move more into this space over here. The area of a circle. I like this one in my own classes as well. We ask, every student knows the area of a circle, or many people know the area of a circle is pi r squared. But if you ask them where on earth did that come from, they'll say, well, that was on the formula sheet, that's how it's always been. They might vaguely know what pi is in terms of circumferences and things, but yeah, that formula, that's just the way it is. But the reasoning to getting that formula is quite a fundamental principle within mathematics, which if they haven't grasped with a simple thing, they're not going to grasp the more complicated notions. So here, if you appeal to their own intuition, you say, well, if you have a circle, how would you find that area in terms of things you already know? You can divide this thing up into little segments, all right? So you could take a few, but the more and more you take, the closer you're getting to the area of that circle. So there's an idea of going from finitely many to infinitely many. And as you do that, these little curves here just land up being a straight line. So the area of the circle is the area of this rectangle. And the radius of this thing is r, and the length here is pi r, and that's how we get the area of a circle. This explains really neatly when we say, well, the area under a curve that is positive is given by an integral. In that we have limits, this idea of moving from finitely many to infinitely many. We're adding up little areas. Here we're adding up areas. Products like that are areas. And that's how we motivate the definition of an integral. With that, then one is easily able to find the areas of other shapes. One even can move from areas to volumes. And that whole principle moves along with you. The final example is that of trig. Trig for students is a table of things they have to learn. All right, so you don't need to go through all of these. Maybe you remember some of them. A whole lot of formulae, and mostly they say to us, do we have to know all of those things? Without knowing why or where, trig is just a nightmare. Few students have the perception that trig is about measuring triangles, measuring angles, finding ratios between sides and angles. When I was thinking about some of this work, I found a paper that said, written in stone, the world's first trigonometry revealed in an ancient Babylonian tablet. So I played with this a little bit, and I thought this is a nice exercise to put into this framework. So you start with something you've read somewhere, and you see it's all funny things, but they've transcribed it into numbers like this. And you try to understand, so what's really happening? What is the connection with the trig that you know? So strangely, they're referring to a rectangle where you have a short side and a diagonal and a long side, and in the numbers here, they've given b over l, d over l, then d over l squared, and then b and d, but they didn't give l. Obviously, you can find l. I put the values in there. all right, because that's what Pythagoras does. So they're given Pythagorean triples, as referred to. And if you add this thing squared plus this thing squared, you add this thing squared plus 1, you get this column over here. And believe you me, you can do that. Excel showed me that I put it all together. But moving towards what we understand better, actually what they did there was to give the Pythagorean identity. So that one became tan squared plus 1 is equal to sec squared. And why they gave us b over L and d over L is they were giving us the tan of this angle up here, or the sec of that angle. So that was quite fascinating. But then students come along and say, well, actually in chemistry, I'm dealing with these red and wonderful compounds, and they're talking about angles here that are bigger than 90 degrees, and here we've been dealing in this little rectangle where everything is at most 90 degrees, so what's going on there? So yet another way to think of trig, and thinking then moving towards functions, is that if you take a unit circle, the point on the unit circle is given by those two trig functions. And when you trace out this point along the circle, you're tracing out these curves. And from this, you get the very many other identities that are not just the Pythagorean identities. You can find the sign of a sum of two angles, so you can go beyond 90 degrees. And that then leads us to be able to easily move to radian measure, to define trig functions in the Cartesian plane, even as power series or Taylor polynomials, and then motivating complex numbers. So those are the examples. You're off the hook now with the maths. All right, so I've tried to argue that orthogonality is key in trying to help our students move from their more intuitive understanding, a more intuitive reasoning of mathematics towards more of a mathematical reasoning. And what one can also look at is if I looked at the NVT results, typically a student who has a basic achievement level would be working in this, maybe a little bit over here with their own reasoning, but not necessarily being able to answer the questions too well. Then the students in the more intermediate level are able to move between these quadrants and a little bit into the conceptual understanding. And the proficient students are able to move around these quadrants interchangeably. And these are the students that typically can do better at university. So I've tried to illustrate here that the advantage of the insights of this plane are much more useful if we think dynamically and not statically. So the idea is you move around these quadrants in no particular order. It depends on the problem that you're encountering, but you should be able to move backwards and forwards. And this year, to some extent, we have tried to incorporate this into the curriculum integrated differentiated support for first year maths. So I've got my module coordinator here, Karen Hull, and we designed some of the tutorials using this idea. And I must say I taught the course in the first semester, and some of the students, before their first assessment, they decided we're not going to engage with this, and came to ask me, so how should we study for the exams, even though we might have encouraged them to go through this process. I asked if they'd engaged. No, they didn't. They just keep on with their own methods. But through that process of actually working on it, the students that came to see me realized the value of going around this, the value of the kinds of tutorials that we set, getting them to understand the basics, why is it working like that, and then being able to move to other spaces. The success of doing such a thing can only really be evaluated in their future years of study. Will they be able to retain this understanding longer than in the ways that they had before? So I claim that navigating between these various quadrants or these various perspectives of mathematical proficiency will help to develop a more positive disposition towards maths and hopefully make our students be far more effective in how they reason, so they know how, but also what they know. Do they know that things are the case? Do they know why that they're the case? So taking this a bit further forward, I do very aware that not all of our students are doing maths for the purpose of maths. And they may resist this kind of shaping that we are trying to do. They might ask us questions, where will I use this maths in my future studies or in my future career? And although this might seem like they're asking a question about a particular concept or a particular method, they're actually asking us perhaps about the level of formalism that we're doing. They're not quite sure where that is. And some quotes that I've read is that the more students believe the mathematics is integrated and integral to their degree course, the more motivated they are likely to be, and the more meaning-oriented their approaches to studying will become. The papers that I referred to, or that we referred to at the start, they give a phenomenological analysis of students' perceptions of the usefulness of mathematics in their studies and in their future careers. It was a study, including a South African there, of 1,182 students across 5 universities in 5 countries. And I only found this after I had developed my framework. The responses were grouped into 4 categories: the don't know, procedural skills, conceptual skills, and professional skills. So how can I bring this more into what I've done today? So for this, I've taken inspiration from this book, The Soul of a University, Why Excellence is Not Enough. And I argue that we're being challenged to achieve excellence with purpose, and for this, that orthogonality is going to be key. So with regards to excellence, we might ask, what is a mathematics module or graduate good at? And with regards to purpose, we might ask, what is a mathematics module or graduate good for? These 2 questions were originally posed for academic work at large in this book, and as a recommended thought experiment of any university. So I've applied it specifically then to mathematics. And in my total talk, I hope, in October, I'm going to consider an orthogonal framework which uses another plane or another dimension of LCT called the autonomy plane, together with this insight. So the autonomy plane is going to analyze the good at versus the good for. Yeah? And this insight gives us a finer analysis of the good at. So we know, what do we know versus the know-how. And I hope that in that way we will be able to take tours around this in their terminology, autonomy tours, to achieve excellence with purpose in the learning and teaching of mathematics. But I also believe that that conceptual framework will be useful for other fundamental disciplines where we often challenge what is the purpose of doing this. So thank you very much.
Anybody is not signed, the idea is registered. Any questions or responses? I would like to share the article, so tell me that topic for last time. Yes.
I find your framework very clear and there's nothing I can disagree with. But the question remains, how do we achieve that students become more mathematical? What is it from the teaching side that is most productive? So what kinds of tasks, what kinds of questions do we have to ask them? And then as we get at lower levels in mathematics education, it's always the curriculum and the time question. So how much time do you afford students on perhaps moving from the intuitive plane to somewhere else before you say, oh, you're not achieving at the pace we want to achieve, and therefore you're out?
So some of the things that we've done with this differentiated support in the first year is that the students that are able to move around these different insights on their own, they certainly can carry on doing their things, but of course some enrichment might be helpful for them. But for other students, one would need to take them through that particular process. So I think that the example I used with areas, the area of a circle, is something that I've done in class. Okay, I haven't followed up in the second semester to teach them further, but students actually came to understanding that, and my hope is that by taking that basic example of the area of a circle, whenever they're thinking of the areas under a curve, they will always go back to that space. So I think the way we've set up the tutorials, and you're welcome, I didn't show any now because that's, it's too much complicated maths there. We actually gave them some basic procedural things that they needed to come to grips with to understand. We asked them questions. Why is it like this? What did you do here? What happens if you did this? So, and then move them into the more conceptual things where they might actually have to do a little proof, but they've already taken that initial step, and then linked it up to saying this is where you will see this again in future topics. We've also introduced the idea of a project. They do that one per quarter, is it? Yeah? And usually mathematicians don't we have a textbook, and at the end of each chapter there's a project question, so we never use that. The team of first year lecturers, they took this, we've been doing it for 2 or 3 years now, and one of the lecturers has spent time formulating projects that are of interest, using some of that, but also using some other things. And some of them have been more mathematical, some of them have been more applied to something that's topical, like the petrol price or whatever, so that they work with that and actually engage with it. And the way it's set out is they go through various processes. The question is, how do you assess that? Each one of those is assessed at least once, or at most once, in their various assessments. So the first term is in assessment 1. They know they're getting that project. It's interesting how few study it. Yeah? We make a small change. So you might be dealing with a whole pile of boxes and a circle on the top. You change it to dealing with a whole pile of boxes with a triangle on the top. All right? So it's a very small change, but they would have had to engage with that project to know what was useful information. And some of the changes that we put in have no impact on the solution, but if they really understood it, and it's almost free marks for them, but they needed to get into it. And you have students come and say, please, I just want to see, is this right? I said, but you should be able to understand if it's right, if you've gone through your process. Okay, so off they go. They come back a few hours later and say, yes, we now know our answer's right. So that is the process. That thing of, there isn't just a memo that I can check. It's more about, I've worked through these steps, I've gone through that reasoning, and you're taking me on those steps to get there. So those are just some examples we've used in first year maths. And some of my colleagues in extended degree programs, so they're dealing with the bridging maths course, they're putting some of this into online resources. So they're trying to take like the notion of continuity, try to find something that students can relate to, and then build it into getting towards a formal definition so that they understand that. So it's a long process. Maybe we do less maths and not so much maths. Yeah?
More questions, comments?
To make a comment quickly, we're thinking about the answer now and what's just been asked. I think what I like about this is it moves us out of the frame of reference in which we focus so much on teaching methods. What little thing am I going to do year or whatever into a more systematic look at a discipline and what's going on there and what we want students to really achieve and how we can do that. We need to turn this back to all those questions of what happens in class, but doesn't get us stuck in the space of just trying new ways of teaching something.
We also ask the students sometimes, I've shown them this framework, I've shown the all the first years have seen the framework, and you ask them to take anything, any concept that they really like and to try and populate this. It's quite a learning process to just do that, and in that way you're actually learning something as well. It's a different learning to maybe answer, we're not learning something to answer the exam. You notice I never mentioned any pass rates. I don't do numbers. I'm more interested in that learning experience. Yes.
Will you teach this content by using this? Aren't you worried about the fact that they don't know everything that you're hoping to teach them?
What do we do in first year maths? So I teach first year maths, all right? I'm also thinking how to do this in further years. But in first year maths, we don't teach such a lot. We spend most of the lecture going through tons of examples of the same thing. And all they're doing is just writing it down and not getting any new insight. I do fewer examples but go through this process more so that then it doesn't matter what example you give them, where they start in that in any of those quadrants, they should feel empowered to do it. It's about giving them that confidence to move beyond that fear of maths. I can speak from experience. I have lots of stories from when I was a student, a learner. So I was in grade, standard 2. You did word science. I absolutely hated word science. You had to take those words and put them in maths, and everybody seemed to know whether they needed to multiply or divide or whatever. And you can speak to my mother. She's still alive. She will know how many days I was in tears trying to figure out what was going on. My dad would come home from work. Really, he couldn't believe how much patience my mother had. So neither of my family had a degree. But I wanted to know why it was happening. So you look back and you say, but no teachers were doing that for you at the time. You just had to all know this, and if you didn't know it, you were left behind. As I went through school, the more independent you became, the more I got into understanding this stuff. So that I can speak from my own experience, this thing of, why is it like that? Some of these things I was never taught at school. You don't know them. And if you don't have that space when you engage with it, it's a bit of a challenge. So my hope is to try and create some online resource when my time allows, when I'm retired, that you can help students to just help themselves in a way. Because I feel so badly for the students that are getting 90% in the fail. It's because they're sitting in the procedures and they never get beyond that. They know that extremely well, but they have no idea why they're doing it. They stopped asking the question why. And also the purpose thing, this thing of maths for purpose. I think that I'm also very excited about playing with that stuff. So that's kind of...
Which actually, it leads me to my question. Wouldn't it be interesting, I know it's almost impossible and a nightmare, but wouldn't it be interesting to see after this really, really important intervention, whether previous graduates of the program actually are different to graduates who've been through this thinking, this analytical process, and to try and track them down and ask them what they graduated for, what are they doing, how did it, and see. I know it's almost impossible, but it is something we're trying to do in our program, and it's a hell of a challenge to institute curriculum changes and program changes, and then to see if your intervention actually worked. But it's really nice.
Now we have the challenge too that we have such a wide spectrum of students. So there are those that are doing maths for the sake of mathematics. There are those that are doing maths for some other purpose, and how do you accommodate all of those needs? Because if you start going into the chemistry example, you end up having to explain the chemistry and you didn't do the maths. So one needs it to do it through other means, through projects or something else. Where there's part of that discovery. What do we do as academics? We discover stuff, and that's why we introduce the project to create that space of discovery as well.
That is not just like, I have to write this answer down, and it has to look as perfect as in the textbook. Yeah. Yes, Anton.
Actually, I have a comment on one of the previous questions within the question. This concern of ours for not covering all the work is a real concern. But still, we let students carry on with the things. They don't know. So, I think I share your view that it's developing the right skills is more important than collecting the right memory of solutions, not knowledge, just memory of solutions. So I think the approach that I like about the approach is it really develops skill, develops the student. But you understand it correctly that in practice this means that in your teaching, in your formative assessments and in your summative assessments, so you must make sure that you start in all of the quadrants and work to it. So I think it's one easily falls into the pattern of choosing one group and just teaching one group and assessing one group, and that's why we fail here. Because we've been looking in our faculty at a tool to assess the assessments. How do you assess the quality of your assessments? I think I'm understanding some of the things that Karen was trying to explain in that tool, because we're using some of these concepts, and again, it's making sure that you have all the routes covered, not only dominating on the one route.
Because if you keep going one way, the student's only going to go one way.
Yeah, and they don't learn the skill of the other way, because it's more difficult to master, or it's more difficult for them when they get lower marks. But you intentionally have to teach formative assess and summative assessment all quality.
Also, what I find quite exciting is the fact that because we all think differently, our way of thinking is going to be different ways around the quadrants. And if we can expose those students to actually looking at it from my perspective, I can always say, oh, this is easy. You think like me, so you're getting it 100%. But it's to make that person that doesn't think like me get to think like me.
And to take them on that journey, to have that confidence that I'm actually moving towards presenting something that is using mathematical language, writing their own reasoning. It's not about watering down the maths either, but it's that step. I've taught third-year math students a very abstract course in topology, and taking them on that path. They were not students that were doing topology, they were physics students. They were doing topology, but they were actually physics majors. And I remember that absolute satisfaction of them. They had to struggle. I didn't give them memos. I don't do memos. I'm not into memos. But write it down with, okay, what's happening. And I would go through each student's process. And at the end of the year, the external examiner said, they can see that these are the students' groups. They haven't learned these off by heart. And for me, that was just amazing. And I wasn't doing this kind of stuff then, but that's how it's part of the way I think my own mathematical teaching but yeah, students start in different spaces.
If there are no more questions, then we thank you, Ingrid, for coming and sharing
Thanks.
this with us. I'm very excited about it. And thank you to everybody who came. I was meant to tell you what Auxin is about, but I hope you all know what it is. In my earlier introduction, so we hope to see you at the Auxin.